So suppose we have uniform charge density lambda distributed across an x-axis, and we're going to assume that this is going to be an infinite line of charge. And what we want to do is find the electric field at some point y, some distance y, above the x-axis. Okay, so this is the problem that we have. And once again, always start with this equation. The challenge is to set this equation up into a form that can be integrated or at least solved by a computer. And so, following the general prescription, remember that lambda is charge per unit length, or in this case is going to be an infinitesimal amount of charge per unit length, infinitesimal length dx. And as a result, we can say that dq is going to equal lambda dx. Now remember that our dq is just a small representative piece of charge, right? The line carries an entire, the line carries charge uniformly distributed about it. And we want to just basically kind of take a little tiny chunk. And this chunk is going to have width dx, and it's going to have amount dq. And we're going to say that this is a distance x from the origin, which is right here. And so, with that in mind, remember that the vector that connects your source charge to your field point is denoted by this vector r. And when you have an infinite line of charge, what you can do is exploit some symmetry. Now remember that since we're assuming our line is positively charged, that the electric field contribution from this little tiny sliver of charge dx right here is going to contribute field dE, this blue vector. Okay, and its components, you'll have a vertical component dEy and a horizontal component dEx. But you'll notice if I take an identical chunk, an equidistant position along the x-axis in the opposite direction, it will also have its own r vector, and it will also produce its own differential amount of field dE, and it will also have components dEy and dEx. And you'll notice that the dEx components are going to cancel out. And as a result, we only want to keep the vertical components. Okay, so we've defined our r vector here, and we need to get r squared to insert into our equation. So we can automatically insert lambda dx for dq, and we want to get r squared. So by the Pythagorean theorem, we note that the magnitude of the r vector is going to be x squared plus y squared, square rooted. And so then r squared is going to be x squared plus y squared. And we're taking, if I define this angle right here to be theta, okay, then that means by the vertical angle theorem, this angle is theta. And by the alternate interior angle theorem, this angle is also theta. So in terms of this right triangle right here, okay, in terms of that right triangle, the vertical component is going to be the cosine component. And so, with all of that in mind, we arrive at this expression. Okay? So I'm substituting lambda dx in for q. I'm substituting x squared plus y squared for r. And I have cosine theta to denote that this is going to be the vertical components that are adding. And I technically should put a j hat out here, and that's fine. And because our line is infinite, our limits of integration are going to be from negative infinity to infinity. Now, this is all well and good. And one thing to note, all right, remember that cosine of theta in terms of this triangle, sorry for the sloppy artwork, imagine those are straight lines. In terms of that triangle, cosine of theta is going to be y over r. Okay, and so cosine of theta is y over r, or that is going to be y over x squared plus y squared to the 1/2. And so when I insert y over x squared plus y squared to the 1/2 in for cosine, I substitute this in right here, and I'm going to get a y in the numerator right here, and I'm going to multiply this by the x squared plus y squared to the 1/2, and that gives me x squared plus y squared to the 3/2. So this is my final result right here. So now I have something that can be integrated, at least in principle. Okay, and I've set it up such that my components are correct. My horizontal components are canceling out, so I'm not worried about calculating those. I'm only worried about the vertical components. And so, once again, inserting our unit vector. So what this means is that my net field, what color should I use? Let's use this. My net field, and we'll use that. My net field will be up along that direction. Right there. Okay? And so, with that in mind, we now have to decide how we want to integrate this. As I've mentioned, popular techniques for using websites would include things like Wolfram Alpha or integralcalculator.com, and those are fine to use. But if you need to do this by hand, here's how I would do it. Right? I'm going to use what's called a trig substitution. So, remember, what we're going to do is we're going to define tan theta to be x over y. And we're getting this from this triangle right here. Right? So, I've already defined theta to be this angle right here. Okay? I've already defined theta to be that angle right there. And tangent of theta is opposite over adjacent, which means x over y. Right? So tan theta is going to be x over y. And I'm going to rearrange that for x because my integral has a dx, so I want to substitute theta for x. I need to substitute my x out, and I need to get theta into the integral. So first things first is to factor out, okay, factor out a y from the bottom, and that's what I've done right here. And so, if this step isn't quite clear to you, let's see how this works. I have y squared plus x squared to the 3/2. And what I'm going to do is I'm going to factor out a y squared. And so this is going to be y squared 1 plus x squared over y squared, all still to the 3/2. And my y squared to the 3/2, the y squared and the 1/2 in the power are going to undo each other. And so I'm just going to be left with y cubed. So this is going to be y cubed times 1 plus x squared over y squared to the 3/2. But 1 plus x squared over y squared, x over y is tan theta, right? X over y is tan theta, and so 1 plus x squared over y squared is equal to 1 plus tangent squared theta. Okay? And so that is where the trig substitution comes from. Okay? So that is where the trig substitution comes from. But this is to the 3/2 power. Now, there's another trig identity that says that 1 plus tangent squared is secant squared. So 1 plus tangent squared turns into secant squared, and it's still to the 3/2. So again, the squared and the 1/2 undo each other, and I'm left with secant cubed. Whoop. So the denominator is going to be y cubed times secant cubed. Okay? Now, so that takes care of the denominator. The denominator is going to be y cubed times secant cubed. And actually, I didn't want to do that. Now for the dx. Okay? The dx, I'm going to get y. I still have a y from tan theta, but if I take the differential of this, y is held constant, so it doesn't change, and therefore only theta is going to be the angle that's changing, or the variable that's changing. And the derivative of tan theta is secant squared d theta. So d tan theta is equal to secant squared d theta. Secant squared theta d theta, technically. Okay. So my dx turns into y times secant squared theta d theta. Okay. So that gets substituted into my expression. Now remember, we have a y already in the numerator from the cosine component that doesn't cancel out. So I have y over effectively y cubed times secant cubed. Okay. So I have y over y cubed, and so y over y cubed goes to y squared. But then I get another y from substituting in for dx right here. So when I substitute in for dx, I get another y, and the overall result is going to be just simply 1 over y. Now, I factored out my Coulomb's constant and my charge density because they're both constant. So out in front of the integral, I have just k lambda over y. And inside the integral, things boil down quite nicely because the trig functions that are left, I remember I have secant cubed in the denominator from the tangent substitution, and I have secant squared in the numerator from the dx, and secant squared divided by secant cubed is 1 over secant, and that's just cosine, right? So in the integral, I'm left with cosine theta d theta after I cancel out the y there with the y squared there. And so I just have k lambda over y, integral of cosine theta d theta. Now the only thing that's left are the limits of integration. Well, the limits on x are from negative infinity to infinity, right? And these are inclusive. And so, if I look at this definition of tangent, or what I've substituted for x, rather, okay? So x is equal to y tan theta. So what must theta be when x is equal to negative infinity? Okay? Well, if you recall, the tan function okay? If you recall the tan function, the tangent goes to negative infinity when it approaches negative pi over 2. Okay? And it and so this goes to infinity asymptotically toward negative pi halves. Okay, and likewise, as it gets closer and closer to pi halves, it approaches infinity asymptotically this way. So if I let x equal infinity, then this expression must hold. And remember, y is finite, right? My y's are finite. They're just a number. That's just the distance above the x-axis we're taking this measurement. And as a result, it's just a multiplicative constant is what is going on there at the end of the day. And so the only things that matter are the tangents. Not just the tangents, but where tangent goes to infinity and where tangent goes to negative infinity. And those occur at negative pi halves and pi halves. So my end result is that I have negative pi halves to pi halves on my integral here. And the integral of cosine is just sine, so I'm going to evaluate sine between pi halves and negative pi halves. And the sine of pi halves is 1. The sine of negative pi halves is negative 1. So this just becomes 1 minus negative 1, which is 2. And so my end result is 2 times k times lambda over y. And the electric field of an infinitely charged wire then does not die off with the inverse square law. Okay, it is just inversely related to how far away from the wire you are. Right? And again, that's just because you have a lot more charges. It's not just a point charge. You have a lot more charges that are contributing to the field. So this is your result, 2k lambda over y. And this is a pretty standard result. It's a regular exercise, but here it is. This is how you would do it if you needed to do it by hand. Now, there's one remaining topic that I would like to address, and that is an addendum of vectors. And so far we've kind of hand wavy ish talked about the unit vector r hat and the r vector here and so on. But how do I compute this r vector rigorously? Okay, how would I compute this r vector rigorously? Okay, one technique to do it is to define a vector capital R, and if I define a vector capital R, I'm going to define this vector as a vector pointing from the origin to my field point. Okay, so it is the red vector here. It is this vector right here. And I'm going to denote a vector, call it r prime. And r prime is going to be the vector that goes from the origin to my source charge. Okay? And it turns out your r vector, the lowercase r vector, is just the difference between these two vectors. Now remember how vector subtraction works. If I have two vectors, say a and b, and I want to write a minus b, then that is the vector that starts at the tip of b and goes to the tip of a. So this lowercase r vector starts at the tip of r prime and goes to the tip of r. Okay? And so, with that being said, we would have, then in this case, my r vector would be my y value, the height above the x-axis in the j direction, and r prime would be x in the I direction. Okay? And so r, it would equal y in the j direction minus x in the I direction. And r squared, to get r squared for the denominator here, what you would do is dot this vector into itself. Okay? So, to dot this vector into itself, what you do is we would take y in the j direction minus x in the I direction and dot that into itself, y in the j direction minus x in the I direction. And the result would be y squared j dot j minus 2xy j dot I. These need to be j's, not i's. And this would be dot j. And this would be plus x squared I dot I. So these are dot products, right? And remember, j dot j is just going to be 1. I dot j, or j dot I, either way, is going to be 0 because these vectors are perpendicular, and so the dot product has no meaning, right? It goes to 0. And so what you're going to be left with is y squared times 1, j dot j is 1, plus x squared, I dot I is 1, and this is just y squared plus x squared. Now, I can also write my unit vector as my r vector over the magnitude, right? And so this would be y in the j direction minus x in the I direction over x squared plus y squared to the 1/2, right? And as a result, this would then, if you're doing this rigorously, this would then get put into your integral. So you would have something that looks like this. You would have an integral, bring k and lambda out front. You would have, if you weren't doing a trig substitution yet, if you were still setting things up, so you would have y in the j direction minus x in the I direction dx, because that's the variable we're integrating over, and dq was lambda dx. And I would have in the denominator r squared times this, which would be r cubed. And the magnitude of r would be x squared plus y squared to the 1/2. So r cubed is x squared plus y squared to the 3/2. Okay, and for the moment this would be from negative infinity to infinity. And so now you have both components. So this splits into two separate integrals. Your y component would be written as y dx over x squared plus y squared to the 3/2 in the j direction, and ex would be equal to x times lambda x dx x squared plus y squared to the 3/2 in the I direction, right? And these are both from negative infinity to infinity. Okay? And so these are your two components. Now the claim was in the original derivation that the I component, or the horizontal components, the x components, would cancel out, right? And here we're arguing this by symmetry. Here you would be able to argue it mathematically. This integral goes to 0. How do I know that without doing any math whatsoever? I know that because this is an odd integral. My limits are symmetrical about the origin, and I have an x right here, and x is an odd function. Linear functions are odd functions, okay, especially when they don't have any intercepts related to them. And so, as a result, this integral would spend as much time underneath the y-axis as it would above the y-axis. And as a result, when I add those two areas up, they cancel each other out because one would be negative and one would be positive. So, and you can prove this to yourself. You can do the same kind of trig substitution that we did, and you will find that this integral does in fact go to 0. Or you can use Wolfram, or you can use whatever. But the y component, you'll see is the same result that we obtained by symmetry arguments, but with some rigorous vector work. And so this is the technically proper way to do it, is to use these vectors. Okay, but you can use the symmetry arguments in these simpler cases, right? But especially in your advanced electricity and magnetism courses beyond your introductory course, they will want you to use the vector notation. So it will pay dividends to get comfortable with this technique now. Even if you don't use it too much, at least expose you to it, so when you do see it, it's not so foreign. And also be aware that there are many different types of coordinate systems that you may use to solve problems in electricity and magnetism. The three most common are Cartesian, which is what we're using in this particular problem. You can also use spherical for spherically charged or spherically symmetric type situations, or you can use cylindrical if you have cylindrical symmetry. And so those are the three most common. Those are not by any stretch the only three that exist, but they are the three most common. And so when you use those coordinate systems, what you end up having to do is write the unit vectors in those coordinate systems in terms of Cartesian coordinate vectors, and then do your integrations. Okay, we're not going to go through that process in this video, but we'll just mention it now. But this is the rigorous way to do the problem, and you'll note that this integral right here is the integral that we obtained right here, just using symmetry arguments. Okay, now why do this method, right? Why use these unit vectors and vectors to do the problem? The reason is not all of your problems are going to be able to exploit high degrees of symmetry, and this method will allow you to write down, at least get to the integral for any situation. If you can write down your vectors appropriately, you can at least write down an integral. It doesn't guarantee that the integral is solvable. You may have to use a computer, so forth. But you can at least write the integral down. Whereas with symmetry arguments, you can't always do that if your situation isn't highly symmetric. So that's the advantage. So there you have it. I hope this video has been helpful, and we will see you in the next lecture.